Okay, so let's move on. Let's have some counting principles. Today we're going to talk about permutation. So the idea with permutations is that we have n things, we're taking an r at a time, and order matters. So it's n things taken r at a time, and order matters. Order matters. Whoops, sorry. Order matters. Okay, let's develop this. So the question is, how many ways can we arrange the letters C, A, T? Okay, and so we know from the counting principle, let's figure this out. So the first letter is either a C, an A, or a T. The second letter is either an A or a T. If the first letter was A, the second letter was a C or a T. And if the first letter was T, the second letter was an A or a C. And then what's going on with the third letter? If it was a C-A-T, it was C-T-N. It was an A-C. If the first letter was an A and the second letter was a C, how many letters are left of the third option? Only one. Here it's the T. In this fourth case, there's only a C. T-A, all we have left is C. T-C, all we have left is A. So, and once again, we see order matters. For these words, like you'll see words in parentheses. So CTA is not a word, but we're considering it a word. And so by the counting principle, we said the first way, there was 3 letters for the first choice. The second, there was 2 options for the second letter in the word. And there was 1 option for the last letter, so there was 6. Now, some of you are saying, that's easy to try. I could figure that out, but that's the idea. There's 6 ways to arrange the 3 letters. So, I don't want to say that. So we know it's 6, but I'm going to hold off on second. Let's erase that, or put ellipse. So we want to see 3 times 2 times 1. We can say that's something called 3 exclamation points, which is read as 3 factorial. And so we're going to define a new math thing called factorial. So we're going to call it n factorial, which is n times, n minus 1 times n minus 2, all the way down to 1. And once again, we call this n factorial. Now, 3 factorial, obviously the 6. A couple of things that we need to define. We're going to say 1 factorial is 1, and 0 factorial is also 1. A little interesting. It's a math thing. We will discuss it a little bit more. I want you to think about it. So, let's look at some questions. So if you look on a sheet, you have the first 4 questions. Question number 1. How many different 7-digit telephone numbers can be made if any digit from 0 to 9 may be used and there are no restrictions? So you're like, fine. It's a 7-digit number, 2, 3, 4, 5, 6, 7. There's no restrictions, which means I can repeat. So from 0 to 9, there's 10 numbers. So it's 10 times 10 times 10 times 10 times 10 times 10 times 10. That's 10 to the 7th. These are big numbers. They're going to be calculator questions. Number 2, any digit from 0 through 9 may be used, but the first digit cannot be 0. Fine. Counting principle. We draw it out. The first number, 0, cannot be used, so I only have 9, but all the rest of these I can use, there's no restrictions. Final answer, 9 times 10 to the 6th. Number 3, any digit from 0 through 9 may be used, but no digit may appear more than once. So this kind of begins to take us to the permutations. We'll see in a second. So the first, I still have my 7 digits. I just can't repeat. So all 10 are available for the first option. But what's going on with my second space? Yeah, I only have 9. What's going on for my third space? I only have 8. 7, 6, 5, 4. I only have, so it's whatever this, and what is the answer? This ends up being 604,800. Now some of you might be saying, wait a minute, this kind of looks like a factorial. Hold that thought. It's not exactly a factorial. It's almost. Once again, hold that thought. Part D. Let's see, what does Part D say? The number must contain all the digits 1 through 7. 1 through 7. Okay, so once again, I have my 1, 2, 3, 4, 5, 6, 7. I only have the numbers 1 through 7, so I only have 7 numbers. So I have 7 for the first, because it has to be 1, 2, 3, 4, 5, 7. I only have 6 for the second, 5 for the third, 4 for the fourth, 3 for the fifth, 2 for the sixth, and then after I've chosen 6 numbers out of 1 through 7, I'm just left with 1. Now, this is equal to 50, 40, 5,040, but some of you said, wait a minute, there's some connection here. So the idea is we want to connect. So how do we connect? How can we connect C and D? And so let's take a look at C for a second, because some of you are a little interested in C. Let's take a look at C. So we have like 10 times 9 times 8 times 7 times 6 times 5 times 4. What we could do is, if we add on, it looks like the 3 times 2 times 1 got chopped off. But hold on something, let me get my red marker. Here we go. It looks like 3, 2, 1 got chopped off. Well, we know from math that it can get chopped off by division. And so we could write this as, actually, our original 10 down to 4 as 10 factorial over 3 factorial. Now, you're looking at that 3, and you're looking at D, and you're like, is that a coincidence? No, it is not. This actually is equal to 10 factorial over 10 minus 7 factorial. And this is our definition of a permutation of 10 objects taken 7 at a time. And this is the idea of the answer to C, which is you have 10 numbers to choose from, and you have to make a 7-digit number. That is a permutation. Permutation, 10 objects taken 7 at a time. So if we have n objects taken r at a time, the notation is NPR, and we say that's equal to n factorial over n minus r factorial. And that's the end of permutation. You have 10 numbers, and you want to take them 7 at a time. And also the idea, in this case, in general, there's no repetition. But we'll assume that, and you'll be told that. Let's go on. So, let me pause the video to erase the board. Okay, let's take a look at the sheet for the next question. A bet that picks in the correct order the horses which finish first, second, and third is called a triactor bet. How many different triactor bets are possible in an 8-horse race? Well, You can either do the counting principle, but let's use permutations. We're saying that there's, first of all, there's 8 horses, and we're taking 3 at a time. Obviously, order matters because horse A, horse B, horse C is a different outcome than B, A, C. So order matters. So you know it's permutations. We have 8 horses, and we're taking them 3 at a time. So we can use you can say 8 factorial over 8 minus 3 factorial. Now, obviously, it's going to be a calculated problem. So I want you to figure out in your GDC how to use the factorial. We can do it old school if you want to, or you can, I'll do it old school. You should do this. So it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, this is 8 minus 3, so it's 5 times 4 times 3 times 2 times 1. These go out with this, and we're left with 8 times 7 times 6. Hey Siri, 8 times 7 times 6.
8 times 7 times 6 is 336.
The answer is 336. That's kind of interesting. There's 336 ways that this race could happen in. Okay, let's try another one. The next one is how many 9-letter. Actually, you know what? Let's change this. How many 9-letter words can be formed by using the letters in the word facetious? The reason I like the word facetious is that there's no repetition and it has all the vowels. Well, let's see. We have 9 objects taken 9 at a time, and because they're words, order matters. So we're using permutation. This is 9 factorial. I could change this question around. Let me change the question. How about in 5-letter words? So let's let that be part B. I'll change it I'll change the document. So we have 9 P5. So it's 9 factorial over 9 minus 5 factorial. Use the GDC. Now, something that's a little advanced and they don't ask it anymore is the last question, which is how many 9-letter words can be formed by the letters from the word isosceles? So what's going on with isosceles? Well, an isosceles triangle is a triangle with at least 2 sides. And the question is, how do we find how many different words? Well, your first instinct might say, well, Mr. Adler, it's just 9 factorial, because it's 9 choose, 9 choose 9 is, it's 9 factorial over 9 minus 0, 9 minus 9 factorial, which is 9 factorial over 0 factorial, which is 9 factorial. But the problem is there's repetition. So the idea is how many times does a letter repeat? And you say, okay, Mr. Adler, there seems to be 3 S's, and there seems to be 2 E's. And so the answer would be, watch, you're never going to be asked this, who knows? The actual answer is 9 factorial divided by 3 factorial times 2 factorial. Am I going to ever ask this on a test? No. Is IB asking this on a test? No. Anyway, this is the idea of permutations. Determine if order matters. Determine how many objects you're taking from and how many objects you're taking at a time. Use the formula. Use the GDC. Good luck. Stop this.